Hey everyone, and welcome back to The Explainer. I am absolutely thrilled you're tuning in today because we're tackling one of the most, mind-bending challenges in modern tech. We're talking about teaching computers how to literally see and understand the world around them. I know, it kind of sounds like straight-up science fiction, right? But it's happening right now, in our phones, our cars, and even our hospitals.
Just take a look at this picture. It's a mother duck swimming with her ducklings. Now, without even trying, your human brain effortlessly separates the mother duck from the water from the ducklings, and each tiny little duckling from its siblings. For us, it's instantaneous. But for a computer, you have to remember, it only sees a massive flat grid of numbers and pixel values. So isolating those overlapping shapes is an absolute massive challenge.
Okay, let's dive into this. Our ultimate goal for this explainer is to figure out exactly how we train an AI to do this visual detective work. By the time we wrap up, you're going to understand how an AI learns to look at, say, a chaotic living room and instantly draw these precise, color-coded bounding boxes around a golden retriever, a spaniel, and a cat, all at the exact same time. Now, to pull this off, we first have to realize that this whole visual detective game actually breaks down into two totally different problems. First up, the AI has to figure out the what. It has to answer, what am I looking at? This is classification, picking a category label from a known list, like dog or cat. But the second problem is the where. The AI literally has to pinpoint the object's exact location by spitting out 4 precise mathematical coordinates, the x and y positions, plus the exact width and height of the box.
So how does this start? Well, the process kicks off by feeding an image. Let's use this single fluffy kitten into a convolutional neural network. These networks are usually pre-trained on massive data sets, stuff like ImageNet, which literally has millions of labeled photos. Basically, the network acts like a giant multi-layered filter. It processes the raw image, pulling out key visual features, things like edges, textures, shapes, and effectively translates that cute kitten into deep computer math.
Once the AI makes its guess on our kitten, we've got to grade it, right? To do this, we use something called multitask loss. It calculates a softmax loss, which is basically grading the what to see if it correctly guessed cat instead of dog or, car, but at the exact same time, it calculates an L2 loss. That's a mathematical penalty grading the where to see how tightly those box coordinates actually fit. Multitask loss combines both of those scores so the AI can learn and correct all of its mistakes in one go. All right, moving on to Section 1, the multiple object mystery. So here's the kicker. The real world isn't made up of perfectly centered single subjects like our little kitten. Real-world images are messy. They have a totally variable number of overlapping objects. Suddenly, the AI can't just output one neat set of 4 numbers. It might need 4 numbers if there's 1 dog, or 12 numbers if there are 3 pets, or 100 numbers for a crowded city street. The AI needs to be completely dynamic to handle this. So how did engineers first try to tackle this variable number problem? Well, they used a brute force approach called the sliding window. Honestly, the idea was kind of naive, but logical. You just have the AI scan a small window across the entire image, moving pixel by agonizing pixel, and asking at every single stop, hey, is there a dog in this exact crop, a cat, or just background? But here is exactly where the math catches up with us. Since objects come in all shapes and sizes, that sliding window can't just be one fixed size. It has to check tiny boxes, tall boxes, wide boxes, massive boxes at every single position. So I want you to take a second and guess just how many possible bounding boxes do you think are inside a standard, kind of low-resolution 800 by 600 image? Are you ready? The answer is roughly 58 million. Yep, 58 million possible boxes to evaluate in just one single standard image. Imagine if your self-driving car had to run a heavy neural network 58 million times just to check one frame of video from its camera. You'd crash before the computer even finished processing a single stop sign. The sliding window method just completely and utterly fails in real time.
Which brings us to Section 2. Region proposals save the day.
To avoid completely drowning in those 58 million calculations, modern AI uses something called region proposals. Through algorithms like selective search, the computer uses incredibly fast rule-of-thumb shortcuts. We call them heuristics, to basically just look for visual groupings. Think color changes, textures, or just general blob-like regions. These blobs have a really high likelihood of actually containing an object. And by doing this, the AI brilliantly narrows down that impossible 58 million boxes to roughly just 2,000 highly probable boxes, a real game changer.
Now, what's really interesting about this slide is how we handle those 2,000 narrowed down boxes. Because they were found using those fast rule of thumb heuristics, they're pretty sloppy. They might only cover half a dog. So the AI applies something called bounding box regression. It literally predicts a mathematical transformation, calculating exactly how much to shift the x and y coordinates and how much to stretch the height and width, all to correct that sloppy proposal into a perfectly tight output box right around the object.
Next up, Section 3, cleaning up overlaps.
Okay, so even with just 2,000 proposed regions, we still have a problem. The AI is likely going to draw, say, a dozen slightly different boxes around the exact same dog. To clean up that mess, we use a step-by-step logic called non-max suppression, or NMS for short. The AI looks at a cluster of overlapping boxes and selects the one with the highest confidence score. Then it checks a metric called intersection over union, or IOU. If any lower scoring box overlaps the winning box by more than a set threshold, let's say 70%, the AI just ruthlessly deletes it. It repeats this process until every single redundant box is gone, leaving just one clean, highly confident detection per pet.
And finally, Section 4, grading the AI detective. So now that our AI has successfully predicted, refined, and cleaned up all its bounding boxes, it's time for the report card. How do we actually know if our AI is good at its job? Well, out in the industry, the gold standard for grading an AI's overall accuracy across all images and all object categories is called mean average precision, or MAP. It's a fairly complex metric, but at its heart, it evaluates these object detectors by calculating the area under what's known as the precision versus recall curve.
To really understand that curve, we have to contrast precision against recall. So precision asks, of all the times the AI predicted a dog, how many were actually correct? It essentially measures the penalty for false alarms. Recall, on the other hand, asks, out of all the actual real dogs in the photo, how many did the AI successfully find? You see, an AI has to perfectly balance being right, that's precision, with being thorough, which is recall. To actually plot this grading curve, we have to follow some incredibly strict rules. First, we sort all the AI's detections from its absolute most confident guess down to its least. Then, we check if the detection matches the actual ground truth box, the one drawn by a human. But here's the catch. To even count as a positive success, the AI's box must overlap the human's box by an IOU greater than 50%. If it's even 49%, nope, it's marked negative. It is a rigorous, totally unforgiving process, but it ensures the AI isn't just out there wildly guessing.
And honestly, that rigorous grading is absolutely crucial, because we're not just talking about drawing boxes around cats and dogs on a computer screen anymore. It brings us to a massive, real-world question I want to leave you with. If this AI were analyzing the street while driving your family car at 70 miles per hour, or if it were reading your medical scan looking for tumors, what level of precision and recall would you demand before you trusted it with your life? It's a pretty staggering thought, right? And it's exactly why researchers are working tirelessly to perfect these incredibly complex systems. Thank you so much for joining me on The Explainer today, and as always, keep asking the big questions.